Swayam Prabha. Digital India. Educated India.
Hi, good morning, everyone. Let us continue today we are going to talk about three topics. One is oscillating water column, and on this topic, you guys are going to have experiment lab. Okay, therefore I skip some analysis a little bit. Okay, second topic is the particle off mechanism. Okay. I'm going to go brief review different particle off. Okay, and the third topic I will talk a little bit more, very brief introduction about power electronics. Okay, and the DC-DC converter. Okay, in this way, on Monday, I can talk about control core design. Control core design, you need a certain level idea. Okay, then on Monday, I'm going to also talk about environment and tech economic analysis, community engagement. Okay, basically, our idea about how to drive the research convergence is a newly funded project, and it's just the ideas what we want to do in the next 5 years. Okay, so we talk about point absorber, right? And the buoy, like this system. We also mentioned oscillating surge device, harvest energy from horizontal direction motion. And we briefly mentioned that like a sort of dark, use eager, such kind of device can harvest energy from both horizontal and vertical motion. Okay, so I mentioned another very popular is oscillating water column. This figure shows basically the principle. The wave come in and the water surface move up and down. When the water surface move up and down, then drive one turbine. So that comes from the nature observation. Like for example, in some coast zone, you can some wave come in, the quickly water come up like that, right? So instead of get water, and you put a turbine here. Okay, so actually that is also one of the first application that 1940s Japanese researcher used that to power the lighthouse. Take a look at how it works here. Okay, so and the wave move up and down, right? Then it drive the air. You drive the air out, then go that direction. You say, follow my mouse, right? So if this water surface more down, and this idea, you say this valve open, right? This valve open, then air goes through here. You can say no matter the water surface more up or more down, the turbine air goes through the turbine one direction, right? This way, such kind of idea has been greatly increased, reliability greatly increased. This one, they can use that as a lighthouse power provider or use that to provide a navigation mark. Okay, so such kind of idea is good, but their problem. The problem is you have to valve open, close, right? And reliability is not that high. So that is one type of oscillating water column. And okay, I already showed that how the wave goes through. Okay, so this another one. This is the top one is Professor Falco's design, and the operation since 1999 is 400 kilowatts wave energy converter. Okay, so it's also, you can say, the turbine. So similar principle, the wave surface move up and down, then drive the turbine. And here, this is one device in UK. So it operates since 2000. So it produces 500 kilowatts energy. So the principle is here, same, right? Wheel come in and the surface move up and down, they drive the turbine, okay? And this also drive the turbine. However, different from just now, we saw the turbine, the air goes through the turbine in two directions. Okay, so then we have to this is another one, and it's in Japan, and it's a combination of breakwater and wave energy converter. In principle, is the same. Okay, so this one is Ireland-based company, and they develop different size of device. One device is currently in test in Hawaii water. The claim is 500 kilowatts wave energy converter, and I look into specification. The generator 130 watts is like that. I don't have the test data how much they can generate. Okay, so that type of wave energy converter developed by some research in China. Okay, so this is like a back bend duct buoy. So you can say this water like that move up and down and drive the turbine. Okay, no matter what, all the turbine is a special turbine. What I mean, the air get in and out. What do you think the turbine rotate? You have air in and out. Can you imagine what kind of turbine it is? You will have regular fan, right? Air in one direction, air out another direction, right? So for this turbine, is special turbine, and it's Wells turbine. I will quickly tell you what's look like. Okay, that is another buoy, and this I think one is in Portugal and another Spanish company. So it's like that. The inside the water, just imagine that way. This will increase the buoyancy, right? And then inside that water move up and down. They have turbine here. And sometimes turbine put horizontal direction, okay, and sometimes vertical direction, okay. So this is alternating water column. It can be land-based, it can be floating, right? So this is show the principle, right? So the buoyancy chamber is here. This is more like a heavy mass, and then the air more in and out. There's turbine here, okay. So air in and air out. So that is important concept. Where's turbine? Give me a moment. Where's turbine? Where's is the inventor's name? Okay, and so where's invented the turbine? It's like this way. Okay, so when the air move up the dash line, okay, it drives the turbine, right? When the air move down, they drive the turbine too. Now the turbine rotates in one direction. Right, so it's like that. This is shape is important. You just think that way. Air in and out generate thrust, right? Air out generate thrust direction. Air in generate thrust same direction. Okay, so another thing is impulse turbine, and this is impulse turbine, and you can say there's a guide. Okay. When the air go one direction like this way, so you can imagine that way. This is in that way it generates thrust. You can say, right, push that direction, right. Another direction will be similar and also generate thrust same direction. So the two turbine, they have different properties, characteristics. So here, that is relative rotation speed normalized. Okay, this is efficiency. Okay, so as you can say, where's turbine and you rotate speed. When the speed change and it's bendwise, not bendwise, speed working speed range, it is narrow, right? And this normalized RPM, you can imagine that way. The efficiency here is higher. And this impulse turbine, and it works in broad frequency range, but efficiency lower. There are not active research in the field to say how to design such kind of turbine. Okay, so in that way, no matter air in and out, the generator always rotate one direction, like here, right? So this well turbine is almost the design and in the Spain, Basque country in the north side, okay, and it's called a country, okay, so it's more like a semi-independent place, is part of Spain, okay, so it's like that the air in and out drive the generator. So about that, when they implement that, they put an air muffler. Otherwise, it generates noise, right? They put a huge air mufflers there, the noise is reduced. Okay, so now how to model this system, right? There are two ways to model the system. One way is use the concept we already learned. They called witness piston. You just imagine that you have piston here, and the piston move up and down. When piston move up and down, that is similar as oscillating body system we learned, right? We have the constant added mass, right, which is water surrounding that. Okay, we also have radiation damping. When this mass move up and down, it generates wave, this concept, right? So then it will also have excitation force, right? So such kind of modeling already we learned, then we can model the system. And another way to model that is using the so-called uniform air pressure model, right? In this chamber, you move up and down, the air pressure will be same. So in that way, and the surface is, it doesn't need to be rigid, right? So for this aero, you need an aerodynamics modeling for this one, and as I promised to you, I'm going to skip this detail analysis, and I highlight a couple of points. Okay, so and this modeling is taken from Professor Falco's textbook, including this figure. Okay, so and basically, I tell you assumption first. Okay, then I don't go through the equation. So you have pressure, temperature, density, and the turbine, this surface area, right? Then you have the pressure plus pressure change, and temperature and density, this surface area. You have for mass flow rate, right? You have volume. So then I skip this part directly. There are quite a few pages, okay, and so that we can get a chance to cover some more content. So, and they take the flow rate into excitation flow rate and radiation flow rate. So then write mass flow rate relationship, and eventually have some assumption, use ideal gas condition. Okay, so this air turbine dynamics you normalize based on the rotation speed and pressure and power output. Okay, it's normalized. Okay, so important part I want to point out like that. Okay, so to understand the important conclusion here, I will introduce the flow rate and pressure relationship, right? And usually this is in proportional with some coefficients. The coefficients it can be complex number. The complex number, what does it mean? The flow rate and pressure, there's phase difference, right? There are real part, imaginary part. Real part we call the conductance. Imaginary part we call the susceptance. That is similar as what we learned, and in the system, control system, real part, imaginary part. If you have electric circle, right, you have, for example, impedance, you have resistor, you have inductor. Okay, so now let us say the physical insights here. Okay, so and you want to have, I open here. Okay, one is mass flow rate and dimension pressure and power output. There's a condition to maximize the power output. So there's a similar, say, this resonance condition. Inside the chamber, there's resonance. Okay, and there's a damping condition. In principle, is same as what we learned the point absorber case. You want to maximize our power output. The certain there's resonance. Okay, then there's damping condition. Then you can maximize our power output. So anyway, these two approach, and there's a relationship. Okay, basically, and this radiation damping and how is it related together. Okay, two ways. Okay, so added mass here, how is it related? Okay, and the excitation force and the excitation flow rate. Okay, so I skip the detail, and if you have interest, I suggest you read Professor Farkow's textbook. Okay, and he's an expert in this field. Okay. So there are also time domain analysis. Okay, I skip this technical details. Okay, it's very interesting the modeling part. Okay, so now with the, I will continue next topic about power takeoff. Okay, right, and this is backward bend duct buoy. So this is usually called a BBDB. Okay, that is very popular design here. Okay, so and his question just now is that design we don't have such kind of bend duct. So anyway, different design. Okay, and you can read some literature why they put some such kind of bend. Okay, so this is another design, right? Just like that way. Oscillating water column, there are many type of different design, even the turbine, and you can, this is turbine, this is in rotation, this is fixed, right? And even there are many different turbine design, and for example, Professor Farcow and his colleague Professor Gauta at Portugal, they design some active vent, and then they can active, if air go one direction, they adjust the vent angle dynamically and then get better efficiency. Okay, so there are some active research. We also have some research how to design this guided vent, and so that reduce the vortex in the system, improve the efficiency. Okay.